episode of Deriving Formulas. As you can see, I already done the first episode about a quadratic formula. Today we're now going to look at a mathematical constant called ln 2. Ln 2 is approximately 0.6931471855. And as you want to know why I have done so many digits of this constant, well, it's because of my fascination with this constant since I discovered the alternating harmonic series. Oh, my cat was meowing. Better let her out. Sorry about my cat, however, because you may have seen it in the Oxford MAT videos. Her name's Coco, and she's older than me in human years. Okay, so why ln 2? Because ln 2 is our first formula here, the sort of alternating harmonic series as it is called. This series sums all the way to ln 2. And I managed to calculate 16 terms and then 15 terms, calculating the average, getting the median, but whatever, couldn't get at least 3 decimal digits of ln 2 out. And the second formula makes use of ln 2's Taylor series. So ln a plus 1 equals to, let me see how you remember the formula correctly, a over 1 minus a squared over 2 plus a cubed over 3 minus a4 over 4 plus dot 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 dot. That's the Taylor series for ln a plus 1. At a is 0, because if you sub in 0, you will get 0, which is exactly ln 1. If we substitute a equals to 1, we get ln 2. However, if we substitute a equals to negative half, so let's see, ln negative half plus 1 equals to ln half equals to, prepare yourself, negative ln 2. So now we're going to derive this series. Ln half equals to negative 1 over 1 times 2 minus 1 over 2 times 2 squared minus 1 over 3 times 2 cubed plus dot 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 dot. Negative ln 2 is the same thing. So ln 2 equals to 1 over 1 times 2 plus 1 over 2 times 2 squared plus 1 over 3 times 2 cubed plus dot dot dot. In summation notation, we can write this as, since this is infinite sum, we write infinity at the top, 1 over n times 2 to the power of n. As you can see, this form will be the heart of all the other ln 2 series except the final one. So, if you may recall this, and we can also easily derive ln a minus 1 over a equals, using summation notation, infinity n equals to 1. Actually, this is also n equals to 1. 1 over n a n. And more powerfully, we can write ln, if you want to take a power, if you're feeling so bold, a to the power of b equals to infinity n equals to 1 b over n a n. As you can see, this form again is the essence of everything that comes before it. Now it all reduces to finding a series of super particular ratios, which is arranged on the form over here, that get their product up to 2. One simple one is 2 equals to 3 over 2 times 4 over 3. Therefore, ln 2, using summation notation, infinity n equals to 1, 1 over n3n plus 1 over n4n. Just saying the first term of the series results in 0.58333 compared to this one, which only gets 0.5. So really, this series does converge to ln 2 faster. Series with definitions like this are called Machin-like series, and they're named after Machin, who produced a formula for pi, which goes like this: 4 tangent inverse 1 over 5 minus tangent inverse 1 over 239. I bothered to remember all these formulas because they're just so interesting. And we can continue, and we can mark it all the way up to ln 2 equals to, and this is my favorite, actually second favorite. Hold on for this one. 31 over n 64n plus 7 over n 81n plus 3 over n 126n plus 20 over n 225n plus 12 over n 2401 to the power of n. This is a series which is really fast growing, and just the first term only gains 2 decimal places of ln 2. And just by using this series, I created a Python program which manipulates these numbers in such a way. Since Python can work with integers with arbitrary precision, we can use it to its advantage and calculate this for 256 terms. This gave me 463 decimal places of ln 2. But look at that! 256 terms giving 463 decimal places. Now, if there's anybody determined to memorize them all, well, there's one last formula which I would like to share. And this involves the hyperbolic sine inverse. And taking the derivative of sine inverse equals to 1 over the square root of 1 plus x squared. You can binomially expand this, and taking the derivative on the Taylor polynomial, which is very easy. So we have, going through all those steps along the way, we now have ln, wait, actually not ln, forget it, ln 2 equals to sine inverse 3 over 4 equals to, wait for this, n equals to 0 to infinity, negative 1 to the n times 2n factorial over n factorial squared times 2n plus 1 times 4 to the power of n times 3 over 4 to the power of 2n plus 1. When you look at that last summation formula, we have the power to compute even more decimal digits of ln 2. Who knows? If anybody can make a Python program which is daring enough to produce this or terms of this, then who knows? You can set a ln 2 record just by using one of these wacky formulas right here. And there's one nice thing about this formula. It can be used to calculate successive binary digits of ln 2. So x naught equals to 0, then xn plus 1 equals to 2xn plus 1 over n. And that gives you the binary digits of ln 2. Side note, it originally sometimes produces a 2, in which case you have to substitute the 2 to a 0 and put a 1 before it if it's a 0. So in this outputs a 2, then if your 2 is here, then you have to change this to a 1 0. Into 1 2, then you have to change it to a 1 0 0. And this continues on forever with as many carry chains as you would like. And that's all for today. ln 2 formulas. You can generate more binary digits than you like. And just on a side note, the first 3 hexadecimal digits of ln 2 are B17.